Hi everybody, this is Mr. Folly and welcome to podcast 1.3 where I can't write, but that's okay. Oh, maybe I need to pick a color. There we go. This is Mr. Folly and welcome to podcast 1.3. We're going to identify a nuclear reaction as alpha, beta, or gamma. We're going to predict the products of alpha, beta, or gamma decay. We're going to differentiate fission and fusion by their nuclear reaction. And we're going to identify a few uses of fission and fusion. We don't have to explain them, just go, oh yeah, that's one that goes with it. So let's start. All right, nuclear fission. Splitting of a heavy nucleus into two or more lighter nuclei and some number of neutrons by shooting a neutron. So what happens is you take a neutron, you shoot it at this big thing, and it goes, it's unstable, and boom, you get a big one, boom, you get a big one, and then you have a certain number of neutrons. Actually, not a certain number, an uncertain number. So in this case, for example, it's 3, it's 2. But notice you have a big one, neutron, bang, big one, neutron, bang, big one, neutron, bang. And what you get are smaller nuclei. What do I mean by smaller? See how this number 235 is the biggest number of mass? These are all smaller than 235. Now the top numbers will add up. 235 plus 1 is 236. 92 plus 141, notice there's a 3 here, plus 1 plus 1 plus 1 is 236. Okay, so the top will equal, and the bottom will equal on both sides. 92 plus 0 equals, that's 92, 36 plus 56 plus 0 is 92. Okay, so that's one way you can tell. If I give you, oh, what's the missing one right here? You can figure out what it is by what's the top number, what's the bottom number, and the periodic table will tell you the bottom number. But again, nuclear fission, neutron for a reactant, and neutrons for products. Okay, that's it. Fusion reactions are a combination of light nuclei to form heavier nuclei. A major fusion reaction occurs continuously in the sun and other stars. So fusion is a little guy. What do I mean by little? That's a small number. That's a small number. Little guy makes a bigger guy. Still not that big, but a little bit bigger. So little guy, little bit bigger. And again, the top numbers, 1 plus 2 is 3. 1 plus 1 is 2. So the top equals the top, the bottom equals the bottom. Now, when man does this, man or people or persons, what happens is they smash these things. They take all kinds of energy by using magnets to accelerate this around fast, smash it into another one, and kaboom, you have yourself a little bit bigger one. Fission is easy, but fusion is tough. If you shoot a neutron, charge equals 0. At a nucleus, charge is positive. There's no repulsion. But if I shoot a positive nucleus, at another positive nucleus, remember, like charges repel. Just like when I have Connor and Caitlin be lab partners. They hate each other. They repel each other. All they do is argue, whine, complain, complain, complain. Medical uses of nuclear. Power generation from plutonium-238 is used to power pacemakers. What a pacemaker is it something that makes your heart beat? Makes your heart beat for the very last time. Or was it the first time? Makes heart beat. And it really makes it beat regularly. So you need a little device that will go bzz, 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 to make your heart beat regularly. And you need a battery for that to work, and that battery has to be better than your cell phone because your cell phone lasts almost until 4th hour. And if your heartbeat thing only worked until 4th hour, we'd have a lot of absences in 5th hour. I made gallows humor. That made me laugh. Whoops. Let me go back. Medical tracers are another way. Things are radioactive, so you can check and see where different chemicals go. So if you, all right, Get ready for Mr. Foley's artwork. Here's my eye, there's a nose, there's a mouth. If you eat something and it's radioactive, you can see if you have a problem in your throat because it might have a little leak that goes somewhere it's not supposed to. And a radioactive tracer would allow that, man, that's a big neck, to see that you've got a problem in your esophagus and other things like that. Medical application. Positron emission topography. This is called a PET scan, positron emission topography. It detects abnormalities in living tissues without disrupting the tissue. So if you look at this, you could say, this is a nice, normal, healthy brain. And then this could be Evan's brain after vaping. Okay? And you go, oh, yeah, look, it's not disrupting the tissue, but you notice the tissue's not quite right. Cancer treatment. Cancer cells are cells that are growing uncontrollably. That's bad. So you don't want your stomach to keep making stomach cells inside your body. You want it to only make stomach cells in the stomach area. So what happens is these cancer cells need extra nutrients. They absorb extra nutrients. So we send radioactive nutrients that destroy the DNA in those cells. Now these radioactive nutrients are also called poison. Okay? And that poison does kill the cancer cells, but it also kills you a little bit too. So the idea is because these things are absorbing nutrients so much more than regular things, we're going to put that poison in and it's going to kill the cancer cells before it kills the patient. And as soon as those cancer cells are dead, they stop giving it to the patient. So that's it. Engineering, thickness control, leak detection. So if I have a pipe like this and I'm pumping through something that's radioactive, and I have a little detector here. Here's my little detector, and I have click, 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 click. Oh, that's where the leak is. Okay. Same thing is true for thickness control. If I'm trying to detect which one's thicker, and we can't tell for whatever reason, or we're doing this on a micro nano scale. We have this. We put something radioactive here. Click, 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 click. This one. Put something radioactive here, click, you get a lot less. I hope you know nuclear power is used in bombs, kaboom, and nuclear power is used in power generation, which is a very safe way of generating power without creating any greenhouse gases. Nuclear reactions. 2 conditions must be met to balance a nuclear equation, and I talked about it already. Conservation of the mass number, that's the top number. Conservation of nuclear charge, that's the atomic number, that's the bottom number. Remember, the tops have to be equal. The bottoms have to be equal. So here again, 232 is 228 plus 4. 90 equals 88 plus 2. And these are balanced. This is a yield sign. It's kind of similar to an equal sign, but yields means produces. Equals means is the same as. So this is the starting point. This is the ending point. So it's not the same as equals. Don't use an equal sign, but turns into yields, transfers into, or becomes yields is what we use in chemistry for it. So what I start with 231, I end with 231 and a 0. That's 231. I start with 90, I end with 91 and negative 1. Well, 91 minus 1 is 90. That's the same. Alpha decay. So an alpha particle is a helium nucleus. Remember, helium is this happy little symbol right here. It's got a subscript of 2. It's big, heavy, and positive, and it's got a mass of 4. Now it's big, so that means it's hard to get in. So imagine if you have a tank and you want to run somebody over, but that somebody is in the middle of the I don't know what's in the middle of the school, in the middle of Mr. Geddes' office. A tank can't get there because it's too big. It can't get through the door. Okay, so it's big, heavy, positive, dangerous, but skin can block it. Okay, so skin can block it, paper can block it. Almost anything blocks it. So why are alpha particles, how could they be bad? Well, if they get you right in the, what's that hole in your eye called? The pupil. Oh, so if it gets in your pupil, ah! Or if you open your mouth, okay, here's more Mr. Foley art. I love drawing the nose. It makes me so happy. This is soft tissue. And if you shoot beams of whatever in the soft tissue there that doesn't have skin, you don't have skin inside of your mouth, I think. Wait, check with your tongue. No. Then that is a place that's vulnerable for it. So polonium-209, 84, undergoes alpha decay. Alpha decay means one of your products is going to be an alpha particle. and then you, yes, you, had to figure out what's left. So 209 equals 4 plus something. That something is 205. 84 equals 2 plus something. That something is 82. Now what is this element? Hey, we learned how to do that before. I look at number 82 in my periodic table. Do. Right hand side. Do. It is PB right there in the top of the list. Sorry about that. So that is a sample alpha particle. Beta decay. Iron Man beta. This is what beta emission looks like. It can also be beta like this with a 0, -1. It can just be beta. A radioactive nucleus that undergoes beta emission has a neutron convert into a proton and an electron. Remember, a neutron has a mass of 1. A proton has a mass of about 1, and an electron has no mass. Hey, notice how that top number will stay the same. It then ejects the electron. So neutron turns into a proton and electron, spits out the electron. Higher energy, but it can be blocked by a sheet of plastic or metal. That means it's harder to block. Beta is negative. It's a negative charge, so it's attracted to positive things. Oh, I'm so peppy, I'm so happy. Here comes beta. Beta is massless. It's so small, it's negligible. Uh-oh. No, you can come in. It doesn't matter. Nope, that's fine. Oh, no, you're fine.
I found the card swipe thing.
Oh, okay.
It's in there a few locations, but the one I found was in the Discovery Center.
Okay.
The card swipe thing isn't working yet. Just
Okay.
it should be.
Okay. Cool. All right. So they tell you something works and it doesn't. Okay.
Just thought you would.
Oh, I do. Thank you. Sorry for the little side step. Oh, no, that's okay. I wish I knew how to pause, but I don't. Hey. No, that's fine. For example, hydrogen-3, a radioactive isotope of hydrogen, undergoes beta decay. So I'm going to have 3, 1 hydrogen undergoes beta decay. This is beta, right? So the mass is going to stay the same, 3. And it can't undergo beta decay, 0. They can't really undergo beta decay. But if I have this, then, ooh, problem solving time. Wait, I know why. Silly me, that's the same mistake so many people make. What's 0 minus 1? -1. This isn't 0, you sillies. It's a 2. 2 minus 1 is 1. Oh, so this is helium. Ah, almost tricked you. Just like this guy almost tricked you. They didn't have a heart, and really he has an axe. And who needs a heart if you have an axe? That's on the pod quiz. Gamma emission. Gamma. Nucleus is too high of energy and just releases energy. It doesn't change any way besides releasing energy. Energy is massless, so gamma is massless. Not much of a change for our purposes. It is chargeless and high energy. It takes feet of lead to block it. Energy does cause problems for us. I like to think of this as after Thanksgiving dinner. You have a lot of energy. You've eaten too much, and you belch. You don't change that much, except for it's tasted a little bit. But you don't change a lot. You just released energy. Cerium-141 undergoes barium emission. So cerium, I'll give you back here. Cerium is Ce. 141 is my top number, written like that. And cerium, I'm looking for its atomic number because I don't know it. Cerium, it's 58. So if it does gamma decay, gamma looks like this. Sometimes you put the 00 there. I often do. It's not necessary. I don't know why I do. 141 over 58 Ce. Now, how did I know that right away? 141 equals 0 plus something. That's 141. Little baby Chucky knows that. 58 equals 0 plus something. 58. Little baby Chucky knows 58. Then that's it. All right, review. Fission splits into smaller parts and starts with a neutral neutron and a positive nucleus. It's easier to start. Top and bottom numbers balance a nuclear reaction. Know the properties of alpha, beta, gamma, and that is it. Toodles.